In this video, we're going to be using the properties of exponents to simplify expressions and also to do a real-life word problem. To start off with, let's understand first just some basic notation for exponents. If I have any real number a and I raise it to the nth power, what that means is a is a product of itself n times. So I would keep multiplying a times itself a total of n times. So for instance, if I had a to the third, that would just simply mean a times a times a grand total of 3 times. So that's nothing new. We're going to delve a little deeper in this lesson and talk a little bit about some properties that we're going to use throughout this chapter and beyond, using some properties of exponents. The way I think I'm going to do this is I'm going to do the properties one at a time, starting with the product of powers. And before I give you the general formula for it, I'm going to give you an example of what it looks like in practice. So if I had something like a squared times a to the third, what that would mean, of course, is, for a squared, that's just an a times an a, and I'm multiplying that by a to the third, which is really 3 a's. So in total, there are 5 a's being multiplied, which can be written as a to the fifth. So a shortcut, if you think about it, if I had a squared times a to the third, would have just been to do a to the 2 plus 3 power and get a to the fifth. Just add the number of factors in the first product, 2, to the number of factors in the second product, 3, and you have a total of 5. In general, it looks like this. If I have a to the power m times a to the power n, you can do a to the m plus n power. So this is our product of powers. Let's do another one, power of a product. I'm just going to do it underneath here. So let's do power of a product. If we have the power of a product, let's start off with an example before I give you the formula. If I had a squared, but I was raising that to the third, what that means is I'd have to do a squared times another a squared times another a squared, a grand total of 3 times because it's being raised to the third. And then I guess you can go further and realize that for every a squared there's 2 a's, right? So it's an a times another a times a third a times a, for a grand total of a to the 6th power. The shortcut here is to realize if I have a squared and I'm raising that to the third, I can just multiply 2 times 3 and get my a to the 6th in a much faster and efficient way. So if I have a to the nth power raised to the mth, I can just multiply a to the n times m power. That's the power of a product property, a very important and powerful property. Let's go to another slide and continue with our properties. So now let's talk about negative exponent property. So negative exponent. For the negative exponent property, I'll give you a couple of examples. If I had a to the negative 2nd power, we never really want to have exponents negative. Now, that's usually the case. What I can do to make that exponent positive is move the base a to the denominator and the exponent will become positive. So a to the negative 2nd is the same as 1 over a to the positive 2nd. Similarly, if I had something like 1 over, let's say I had 2 to the negative 3rd, notice how the exponent's negative, but it's in the denominator. I can move that 2 upstairs into the numerator, and the exponent becomes positive. So 1 over 2 to the negative 3 is the same as 2 to the power 3. So in general, negative exponent property says if you have a to the negative mth power, that will be exactly the same as 1 over a to the positive m power. So that's a useful property. Going on, the zero exponent property. This one is pretty straightforward. If I have any real number raised to the 0th power, I get 1. So we'll kind of see that in a couple of examples in a moment. Let's do the power, or before we get to that one, let's do quotient of powers. So quotient of powers. So for quotient of powers, the example I thought I'd give you is this. If I have a to the 3rd over a squared, if we did it the long way, we'd realize, okay, a to the 3rd means I have a times a times a squared. A is a product twice, and I would be able to cancel these common factors, both from the numerator and denominator, and I just get a. Now you could do it that way, but a shortcut is to realize I could have just subtracted the top exponent from the bottom exponent, right? 3 minus the 2, and that would just still give me the a to the 1st, or a. In general, kind of the shortcut and quick way of going about things is if you have a to the power m over a to the power n, you can subtract numerator exponent from denominator's exponent. So that's kind of a nice one. And the last one we'll take a look at, the last property, is the power of a quotient. Power of a quotient property. The example I'm going to give you here is, let's say I have a over 2, and I'm raising that whole quotient to the power 3. Well, what I'm going to do really is duplicate a over 2 3 times, right? That's what it means to be raised to the 3rd. So really I'd have to multiply a times a times a in the top, giving me a to the 3rd, and 2 times 2 times 2 in the bottom, giving me 2 to the 3rd. Which I guess if I wanted, I can write that as a cubed over 2 times 2 times 2 is just 8. But the shortcut here is to realize, hey, I could have just distributed that exponent to both the numerator and to the denominator. So that would be a cubed over 2 cubed. So the shortcut here is, if I have something a over b, so two different numbers in the quotient raised to the power, let's say m, I can distribute that m to the numerator and to the denominator. One last property that we're going to talk about is the power of a product. Power of a product. So let's go something like this. If I had 2a raised to the 3rd, what I would have to do is write 2a 3 times, right, and multiply that together. So if I'm multiplying all those, I can multiply in any order I wish. So I can multiply the 2 times 2 times 2, and I can multiply all the a's together. A times a times a. So I'd get 2 to the 3rd times a to the 3rd, or 8a to the 3rd. Shortcut, distribute that exponent to the 2 and to the a. So I can get 2 cubed times a cubed. Very similar to that power of a quotient property we just looked at. So in general, if I have a product, let's say a times b, and I'm raising it to the power m, I can distribute that power to both factors in the product. So that would be a to the m times b to the m. Let's do a few examples of how to apply this. So in my first example, I'm going to give you numeric values that we're going to evaluate, but what's important to me is that we're actually applying the properties of exponents we just talked about. The first one, let's take a look at if I had 4 squared and then I was raising it to the 3rd. Alright, this is that property where we had the power of a power property. So, or the power of, this is the power of power property. And if you multiply those together, you would get 4 to the power 6. And you could use your calculator to get that, but again, the most important thing to me right now is, are we using the properties correctly? So for right now, I'm fine with that answer. Let's take a look at another one. For B. For the next one, let's take a look at this. If I had 2 squared raised to the -4th, all of that over 2 to the 5th power, I'm going to do the power of a power up in the numerator and multiply these exponents to get 2 to the power negative 8 if you were to multiply over 2 to the 5th. Now what I could do is, actually I have a couple options. Since I have a quotient with the same base, 2, I can take 2 to the top power minus the bottom power, and I can get 2 to the negative 15th, not 15th, but the negative 13th. And remember that negative exponent property? Since the 2 to the negative 13th is in the numerator, I can put it in the denominator and make it 2 to the power 13 downstairs. So it would look like that. Another option you would have had from here would have been to move the 2 to the negative 8 downstairs right away. So I'd have 1 over 2 to the 8th times 2 to the 5th. Then you can add those exponents and get the same result, 2 to the 13th, in the denominator. So hopefully that gives you a little bit of a taste so far with doing this with numeric values. Let's take a look at simplifying some expressions with variables. So let's call this one example 2. Oops. Example 2. Oops, I don't want to be on this slide yet. I'm sorry. Here we go. Example 2. We'll do two problems. A. Let's do 2a to the 5th times a squared, all of that divided by 6a cubed b to the negative 1. Alright, well, I'm going to do kind of simplifying in the top first, and then I'll look at the bottom second. So in the numerator, I notice I'm multiplying an a to the 5th times an a squared, and I can add the 5 plus 2 together using that product of powers property. In the denominator, I don't want to add 3 and negative 1 because the bases are different. The only thing I might do is bring that b to the negative 1 upstairs to make it b to the positive 1, leaving a 6a cubed down in the denominator. So let's rewrite what we have. We have 2a to the power 7 if we add the 5 and 2 times b. I don't need to really write b to the first because it's just b. And then I have 6a cubed. Now I can still go a little further since I can reduce 2 over 6 to the fraction 1 over 3. The other thing I can do is simplify a to the 7th over a to the 3rd using that power of a quotient property. So I can do a to the 7 minus 3, and I'm stuck with a b. And if I do one more step, I think a to the 7 minus 3 is going to be a to the 4th times b over 3. So that would be the final answer for a. Let's do one more together for b. We'll take a look at something maybe a little bit trickier looking. Negative 3a to the negative 1st x squared over 9x to the negative 3rd, that raised to the 2nd. So if I take a look at the numerator, the only thing I could potentially do is move this guy down into the denominator. I wouldn't want to do that with the negative 3. Remember, that negative sign is not an exponent, right? It's just a negative 3. So that negative 3 stays there. And I'm going to write negative 3x squared just for now. In the bottom, I have the 9. I'm going to bring that a to the negative 1 down. So it's really just a to the positive 1 in the denominator. Now here, power of a power property, I can multiply these together to get x to the negative 6th. Now, when you look at this, a couple things can happen. I can reduce the fraction negative 3 over 9 to negative 1 over 3. I can't do anything with the a. There's no other a's floating around, so that a is kind of stuck down there. But what I can do here is a couple things. I can either subtract the exponents, like this, do x squared minus the negative 6 exponent in the denominator, which is really a double negative. It's really x squared plus 6. So final answer would be the opposite of x to the 8th over 3a. Now another option you might have taken, or route you could have taken with this guy, is brought that x to the negative 6 to the top, and you'd have x squared times x to the 6th. Notice how you'd still get x to the 8th there, right, in the numerator. So that would be your final answer there. Before I give you a couple practice problems for your quiz, I thought it would be cool to do one kind of neat word problem that applies properties of exponents. And that problem is right here. If you can just jot down the gist of it, according to Forbes, the founder of Facebook, Mark Zuckerberg, has a net worth of $9.4 billion as of September 2012. To get an idea of just how much money that is, let's calculate how much he can spend every single minute for the next 40 years of his life. Now, in order to do this, we're going to use scientific notation. That's kind of the idea here. Scientific notation is used to help us understand and work with really large and small numbers, and it has to be of the following form. C times 10 to the power n, where that number c is bigger than or equal to 1, but less than 10, and n is any integer. So what we're going to do is start by rewriting Mark Zuckerberg's worth, that 9.4 billion, in scientific notation. Now, 9.4 billion, think about that, that's $9,400,000,000. That is quite a sum of money. The decimal point for that is right there. If we're going to write that in scientific notation, we'd have to move the decimal point to a place where we'd end up with a number between 1 and 10, and 9.4 is that number. So we have to tack on a times 10 to the power of how many spots we moved it, and we moved it 9 spots. So Mark Zuckerberg's salary in scientific notation is that. Hopefully one day you will be lucky enough to have such a large salary you need to express it in scientific notation. And hopefully it's not the other way around. It's so small you need to use scientific notation. That's a kind of math humor there. Maybe it's not very good. Anyway, now what we want to do is calculate how many minutes are in 40 years of time. So let's do 40 years and go back to chapter 1 and do some conversions. 40 years, now for every 1 year, there's 365 days, and for every 1 day, we have 24 hours, and for every 1 hour, we have 60 minutes. Now, let's double check. Our years cancel, our days cancel, our hours cancel, our final units are in minutes. We need to multiply 40 times 365 times 24 times 60. Let's do that now in our if you do, you get the answer of 21,024,000. Now let's put that in scientific notation. The decimal point is there. We'd have to move it 1, 2, 3, 4, 5, 6, 7 to get a number 2.1024. That's my number between 1 and 10, right? Times 10 to that we moved it 7 spots. So what we're going to do, guys, is we're going to take Zuckerberg's salary and we're going to divide it by 2.1024 times 10 to the 7th. Reason why this problem is in this section is I can use properties of exponents to simplify 10 to the 9th over 10 to the 7th. But what I do need to still do is divide 9.4 by 2.1024, and it'd be times 10 to the 9 minus 7 power, right? We would have to subtract those exponents. If we divide in our calculator the 9.4 by 2.1024, I think you get about 4.47 approximately, and that's times 10 to the 2nd. So if we multiply that times 10 times 10, we move the decimal place over twice. That means, guys, Mark Zuckerberg can afford to spend $447 every single minute for the next 40 years of his life. That is insanely rich. Anyway, I hope you kind of enjoyed that problem. What I want you to do to finish the notes are these 3 problems. Please put them in your notes, circle your final answers, and you're going to share them out in your groups when we convene in class next time. If you need to, you can always look back at your notes and my examples to try to see what properties you can use and relate it to something familiar so you can solve these correctly. Good luck.